Now this turbine is very efficient. It works on a head of water. This was designed by John McCormick, International Harvest Services Company. So the water rises only about a foot over the top of the turbine. That's enough head for this machinery. The power is transferred by way of gears and line shafts, pulleys, and cable up to pulley and line shaft. One rule we have is just stay toward the center aisle. There's grass, walk through the field beside that. Okay, you can see where the power is being transferred through the wall by way of a line shaft. You've got a pulley here, belt up to a diver pulley. Now what I'm going to do is I'm going to move the belt from the diver pulley onto a dry pulley so I get power to my center line shaft. The center line shaft was typical of not just machine shops back in the day, but just about any factory. No matter what the power, water, steam engines, air combustion engines, electricity, and well into the 1900s, most factories had this kind of setup. Wherever the seat belt's going, off to the side, that good power, either machinery or tools, in our case, tools. We're going to move on to this other end. Take as many pictures as you like. If I'm in the picture, let me know so I can pull my stomach in, all right? All right, so the machinist that worked here, usually about 12 guys in here during the day, very skilled workers. There's a picture of them out in the lobby. You get a chance to look at them. They don't look like much, but they are, like I say, highly skilled. The highest paid workers in the yard, 15 to 16 cents an hour. That was high pay. They had to go through an apprenticeship. Apprentice actually got paid too, 5 cents an hour. The company kept half of that in an interest-bearing account that paid 6%, pretty good by today's standard. They got that money plus interest back when they finished their apprenticeship. Now what they did here was make small gears, not the big gears you may have seen laying outside. They've been cast somewhere else. Small gears and repair gears. Something like this was worn. They'd have to make a new one. They did some repairs too on gears, and I'll show you that in a second. The center of the gear, right inside the hole, okay? I would have to change the mount out with something like this so I can fit through the hole there. Now here you can see, people on this side can see a little better. There's a threaded rod here. That's part of the automation thing I was saying. I want to turn this on the same way, right? Move the belt over. I've got power to my shaper. And this down here, you can see the threaded rod is turning with each pass just a fraction of a turn. Again, a very slow process. All right. Now you can make these gears in seconds. All right. We'll walk down here, talk very quickly about repair. 1969, to give you an idea of the time period we're talking about. Regular drill press, for obviously for big holes, and move this bit in or out, so you can cut a series of holes and swing it around and do an arc. Holes there on. Now all the tools so far, you can change the speeds. On the drive side, this is on the smallest pulley, so and the driven side, the largest. So this is the slowest speed. If I want this drill to be turning faster and increase the RPMs, I'd have to move that belt on the larger pulley up there and do the opposite down here. Otherwise, I'd move a different size belt, and it wouldn't line up anyway. How can you improve on that? Well, this next machine The size is not impressive, but what is up here. Instead of pulleys, we have cones. Okay? And the drive cone is turning now. If I move that bottom cone up, engage the clutch belt, I've got power to my drill press. Now, if I can move that belt, I can change the speed. All right, now, you can't see it, but there's a fork back there, just like I'm moving all the other belts with a fork, okay? But I can control that fork with these lines. Move to the left, increase the speed, to the right, decrease the speed. So I have a variable speed drill press. Now, I don't know, it's been about, what, 15, 17 years, something like that. Toyota came out with the Prius. Remember the Prius? We still have Priuses.
It is essentially a vertical underwater manhole cover. It's a solid metal and it's about this wide, and it covers the entrance to an underground pipe. Now, you'll notice I'm standing over a pool of water here. This pool is at the same elevation as the water in the mill race. The difference being that it's passed through a trash filter to get rid of the worst junk so it doesn't gum up the works. Now, you will notice that this is an open structure, so the trash can get back in. My only comment about that is I didn't design it. Okay, now, the sluice gate and the accompanying structure weighs about 350 pounds, which is more than I can lift on a good day. But the 19th century was really good at using simple machines to amplify human power. So you have an 8-to-1 gear ratio here, you have a rack and pinion, and of course you have levers here. And that allows me then to lift all of this weight. And for those of you who have an engineering bent, it's really interesting because when there's no water in here, it's much easier to lift this because the water pressure is actually driving the plate against the opening to the pipe and effectively adding weight, or friction anyway. Okay, so now you can start to ripple. Now what I'm going to do is, I'm going to ask you to go down to the black metal railing where we'll get the you'll see the turbine getting started. The turbine is in a black cylindrical housing on your left. Horizontal gear, which in turn is driving the large vertical gear on the left, and that you'll notice is connected to the two shafts that are running to the lower portion of each of the two adjacent middle buildings. You notice the three massive stone walls, but the fourth wall facing the river has nothing on it, might have had a canvas sheet. The roof is quite flimsy. This is really standard barricade technology. Okay, the whole idea is that if there were an explosion, these massive walls would absorb some of the power and they would also reflect the shock wave out across the river. The stone that's used here is absolutely ideal for the river. It's Brandywine Gneiss, G-N-E-I-S-S. It is both hard and resilient. So you'll notice got calibration markings on a wheel and a standard weight hanging from that wheel. I'm going to put about 1 musket shot's worth of gunpowder into this canister, and then I'm going to seal it up. Okay? We haven't lost anybody yet. Then I'm going to seal it up. Okay? And I'm firing it off. The extent to which this wheel deflects is a measure of the amount of power you are getting from the gunpowder. So, this was used as both a quality control tool, allowing you to compare a given grade of product from week to week, and it was used as a marketing tool because a DuPont salesman could take it to customers and compare DuPont's product with the competitor. And guess what? DuPont always won. But there was a reason for that. DuPont had studied chemistry with Antoine Lavoisier in Paris, the father of modern chemistry, and so he had learned all about refining materials, the importance of homogeneity, the importance, using recrystallization techniques, distillation techniques, and so forth. And he applied all that knowledge on a large scale here in the powder yards. And okay. Anyway, so because he used principles of chemistry, he made the best product. Okay, so now I'm going to ask everyone to please stand on this side of the row of brass circles that you see in the floor here. Okay, so everybody would please stand over here. Okay, so we're going to look for two things. We're going to look for how far the wheel deflects, but I'd like you to pay attention also to the amount of smoke that's generated when this goes off. Okay, that was a nice shot. It went all the way around, so you got a fair amount of power out of there. You notice how much smoke is in that box? Okay, now think about this. The Civil War, the American Civil War, took place before the invention of smokeless powder. So you had 150,000 troops on a battlefield, all firing muskets, all using black powder. All that artillery that was used in the Civil War, all using black powder, okay? How would you have even known whether the person in front of you had a gray uniform on or a blue uniform? Okay, how would you know? You won the battle. You could see your hand in front of your face. So, something to think about. Okay, at this point, I'm going to turn you back over to your tour guide.